So one of the ramifications of Einstein's two postulates is a phenomenon called time dilation. We kind of had a brief look at that when I was talking about the introduction. When we talk about time dilation, there's a classic thought experiment that was actually thought up by Einstein himself, involving a train. Okay, so I've got myself a train. Inside the train I have a device that's known as a light clock. Okay? That light clock does one thing. It measures time, like a clock should. So what ends up happening is whenever light strikes the light clock, the clock stops measuring time. So it's kind of a stopwatch, but it's a stopwatch that's sensitive to light. So if it experiences a beam of light, the clock stops. Okay? Cool? Inside, I'm going to have a flashlight, and I'm going to have a mirror. Okay? So up above we have a mirror, down here we have a flashlight, and over here we have a light clock. Okay? So as the train is moving with a velocity, okay, a beam of light is released from the flashlight, it goes up, comes back down, and it measures time. Okay? So it measures some time. Cool? So that's the basis of it. But what ends up really happening is we end up getting 2 points of view inside this train. We have a point of view, let's imagine we have a person inside the train that sees the motion of light behave like this. The other point of view, let me erase the word light clock down here, is that as the train is moving along, and passing somebody standing on the side of the road as the train is, moving along. So imagine we have a person standing outside of the train. What we end up having is here's my light clock, here's my light clock, here's my light clock, and a mirror on the roofs. Apparently it's a Las Vegas train. Okay, and then we have a flashlight. So from the point of view of the person inside or outside of the light goes like this. I'm going to use red. It leaves the flashlight. Sometime later, now here it is going from here to here. Sometime later, it strikes the mirror and then comes back down and strikes the light clock. Okay? So in one path, the light goes up and then back down. In another path, the light is going up and over, and then over. So that's the basic style. Because we've got a problem here. We said that the speed of light is the speed of light. So we said that c is constant, hence the c. Okay. So in this point of view, from this person's point of view, it appears as if the light travels a distance, and we're going to call this height, the height of the train, a distance. It travels this distance in c times t. Okay? And what I'm going to use for t is the amount of time it takes for it to go up here, not back down. I can use symmetry to say that that's about half the time. Okay? But in this point of view, it says it travels this distance. Okay? Which is, I have a distance here, and I have a distance here, so I'm looking at that side of the distance d here, but it also travels a distance vt here. The train is moving in this direction. How far it travels, how much distance it covers within that time is going to be equal to velocity times time. Okay? So we can say it travels a distance of okay? Cool? Now I think I'm going to use a different color the rest of this. I'm just putting this up for now. Decisions are going to come from. What I'm going to do next is I'm going to erase this and I'm going to derive the equation for time dilation. Okay? And I'll use a different color besides red and orange. There's just not enough separation between the two. Cool?